Welcome to another journey through the cosmos here on Nebula Nights. Tonight, we're embarking on something special. We're going to travel through the entire universe, from our cosmic backyard to the very edges of observable space. We'll witness stars being born in clouds of glowing gas, watch galaxies collide over billions of years, peer into the hearts of black holes, and explore the mysterious forces that shape everything we see. This is a voyage that will take us across distances so vast they challenge comprehension, through realms where the rules of everyday physics bend and break, into a universe far stranger and more beautiful than we might imagine. So settle in, find a comfortable position, and prepare yourself for a full night of cosmic exploration. We're about to leave Earth behind and journey outward into the infinite. Before we launch ourselves into the depths of space, let's take a moment to understand where we're starting from. You're sitting here on Earth, a rocky world that orbits a middle-aged star we call the Sun. Our planet spins on its axis once every 24 hours, creating the cycle of day and night that has governed life for billions of years. We're traveling through space at extraordinary speeds, though we never feel it. Earth orbits the Sun at roughly 107,000 kilometers per hour, completing one full circuit every 365.25 days. But Earth's motion doesn't stop there. Our entire solar system, Sun included, is hurtling through space within the Milky Way galaxy at over 800,000 kilometers per hour. The Milky Way itself is moving through the universe, pulled by the gravity of massive galaxy clusters. We're in constant motion, falling through space-time along invisible geodesics, part of a cosmic dance that's been ongoing for nearly 14 billion years. Our address in the universe goes something like this: Earth, third planet from the Sun, solar system, Orion Arm, Milky Way galaxy, local group, Virgo supercluster, Laniakea supercluster, observable universe. Each step in that address represents a jump in scale so dramatic it's almost impossible to grasp intuitively. The distances we'll be talking about tonight are measured in units that might seem strange at first. A light year is the distance light travels in 1 year, roughly 9.5 trillion kilometers. Light, moving at 300,000 kilometers per second, is the fastest thing in the universe according to Einstein's theory of relativity. When we look at distant objects in space, we're not seeing them as they are now, but as they were when their light began its journey toward us. Look at a star 10 light-years away, and you're seeing it as it was a decade ago. Look at a galaxy a million light-years distant, and you're looking a million years into the past. The observable universe, the portion of the cosmos we can theoretically see, extends roughly 46.6 billions light-years in every direction from Earth. This gives us an observable sphere with a diameter of about 93 billion light-years. The universe is actually much older than 93 billion years, you might be thinking. And you'd be right to wonder. The universe is 13.8 billion years old, so how can we see light from objects 46 billion light-years away? The answer lies in cosmic expansion. Space itself has been stretching since the Big Bang, carrying galaxies along with it. An object whose light has been traveling for 13 billion years has been carried much farther away by the expansion of space during that time, so it now sits 46 billion light-years from us. This expansion is one of the most profound discoveries in all of science. In the 1920s, astronomer Edwin Hubble observed that distant galaxies appeared to be moving away from us, and the farther away they were, the faster they seemed to recede. This wasn't because the galaxies were moving through space, but because space itself was expanding, like dots on the surface of an inflating balloon growing farther apart as the balloon expands. The universe has no center, no edge, no privileged position. Every observer, on every planet in every galaxy, sees all other galaxies receding from them. Tonight, we're going to journey outward from Earth, step by step, exploring the structures and phenomena that make up our universe. We'll start close to home in our solar system, then venture to nearby stars and nebulae, expand our view to encompass galaxies and galaxy clusters, and finally, consider the universe as a whole and the mysterious dark components that dominate it. This journey will take us through realms of fire and ice, through clouds of gas glowing with the light of newborn stars, past dead stars compressed to impossible densities, and into regions where our understanding of physics reaches its limits. Let's begin. Our first stop is our own solar system, the cosmic neighborhood we call home. 4.5 billion years ago, this region of space was nothing but a vast cloud of gas and dust, part of a larger molecular cloud drifting through the galaxy. Something, perhaps a shock wave from a nearby exploding star, disturbed this cloud and caused it to begin collapsing under its own gravity. As the cloud contracted, it began to spin faster, just as an ice skater spins faster when pulling in their arms. The spinning, collapsing cloud flattened into a disk with a dense concentration of material at the center. In that central region, the temperature and pressure climbed higher and higher as more material fell inward. Eventually, the core became so hot and dense that hydrogen atoms began fusing into helium, releasing tremendous amounts of energy. A star was born. Our sun ignited, bathing the surrounding disk of gas and dust in light and heat. The young sun's intense radiation and powerful stellar wind began clearing away gas from the inner regions of the disk, but by then, the seeds of planets had already begun to form. Within the disk, particles of dust collided and stuck together, gradually building up into larger and larger clumps. These clumps, called planetesimals, were typically about a kilometer across. Over millions of years, planetesimals collided and merged, forming protoplanets. The temperature gradient across the disk determined what kinds of planets could form in different regions. Close to the sun, where temperatures were extreme, only materials with high melting points could remain solid. This is why the inner planets are rocky and metallic. Farther out, beyond what astronomers call the frost line, water and other volatile compounds could freeze, allowing much larger objects to form. Let's tour this system, starting from the innermost world and moving outward. Mercury is a small, scorched world, barely larger than Earth's moon. With virtually no atmosphere to trap heat or shield it from the sun's radiation, Mercury experiences the most extreme temperature swings of any planet. Daytime temperatures soar above 427 degrees Celsius, hot enough to melt lead, while nighttime temperatures plunge to minus 180 degrees Celsius. The surface is heavily cratered, a record of billions of years of asteroid and comet impacts preserved in the airless environment. Mercury orbits the Sun in just 88 Earth days, the fastest orbital period of any planet, earning its name from the swift Roman messenger god. Venus, the second planet, is often called Earth's twin because of its similar size and mass, but that's where the similarities end. Venus is a hellish world, the hottest planet in the solar system, despite being farther from the Sun than Mercury. Its thick atmosphere, made almost entirely of carbon dioxide, creates a runaway greenhouse effect that keeps surface temperatures around 464 degrees Celsius. The atmospheric pressure at the surface is 90 times greater than Earth's, equivalent to being a kilometer underwater in Earth's oceans. Sulfuric acid clouds cover the entire planet, and lightning storms rage through the corrosive skies. Venus rotates backward compared to most planets, and spins so slowly that a day on Venus is longer than its year. Then comes Earth, our blue marble suspended in the void. From space, Earth appears as a brilliant blue and white sphere, the blue from our vast oceans covering 71% of the surface, the white from clouds perpetually swirling through our atmosphere. Earth is the only world we know of that harbors life, though we're actively searching for evidence of life elsewhere. Our planet sits in what astronomers call the habitable zone, the region around a star where liquid water can exist on a planet's surface. Water is essential for life as we know it, acting as a solvent for biochemical reactions. Earth's atmosphere protects us from harmful radiation while allowing visible light through, and our magnetic field, generated by a churning molten iron core, shields us from the solar wind and cosmic rays. Earth has one large natural satellite, the Moon. Our Moon is unusually large compared to its parent planet, about 1/4 Earth's diameter. Most astronomers think the Moon formed from debris blasted into orbit when a Mars-sized object collided with the young Earth about 4.5 billion years ago. The Moon stabilizes Earth's axial tilt, giving us relatively stable seasons, and its gravitational pull creates ocean tides that may have played a role in the evolution of life. Mars, the fourth planet, is a cold desert world about half Earth's diameter. Its rusty red color comes from iron oxide in the rocks and dust covering its surface. Mars has a thin atmosphere, mostly carbon dioxide, creating a weak greenhouse effect that isn't enough to keep the planet warm. Surface temperatures average -63 degrees Celsius. Evidence suggests Mars was once warmer and wetter, with rivers, lakes, and possibly oceans covering parts of the surface billions of years ago. Where did all that water go? Some froze into polar ice caps and underground deposits, while much of the rest was lost to space as Mars lost its magnetic field and solar winds stripped away its atmosphere. Mars has two small moons, Phobos and Deimos, probably captured asteroids rather than moons that formed alongside the planet. Rovers on Mars' surface have discovered evidence of ancient river deltas, sedimentary rocks, and minerals that form in the presence of water. Whether Mars ever hosted life remains one of the most compelling questions in planetary science. Beyond Mars lies the asteroid belt, a region of rocky debris orbiting between roughly 2.3 and 3.3 astronomical units from the Sun. 1 astronomical unit, by the way, is the average distance from Earth to the Sun, about 150 million kilometers. The asteroid belt contains hundreds of thousands of rocky objects larger than a kilometer across and millions of smaller ones. Despite depictions in movies, the asteroid belt is mostly empty space. The largest object in the belt is Ceres, a dwarf planet about 950 kilometers in diameter, large enough that gravity has pulled it into a spherical shape. The asteroids represent material that never coalesced into a planet, prevented from doing so by Jupiter's immense gravitational influence. Jupiter, the fifth planet and the largest in our solar system, contains more mass than all the other planets combined. This gas giant is truly enormous, more than 11 times Earth's diameter and 318 times Earth's mass. Despite its size, Jupiter is composed primarily of hydrogen and helium, the same elements that make up the Sun. If Jupiter were about 80 times more massive, nuclear fusion would have ignited in its core, and Jupiter would have become a second star rather than a planet. Jupiter's atmosphere features colorful bands of clouds, organized into zones and belts by the planet's rapid rotation. A day on Jupiter lasts less than 10 hours, the fastest rotation of any planet in our solar system. This rapid spin creates powerful atmospheric dynamics, including the Great Red Spot, an anticyclonic storm larger than Earth that has raged for at least 300 years and possibly much longer. Jupiter has at least 95 known moons, ranging from tiny captured asteroids to large worlds that rival planets in size. The four largest, discovered by Galileo in 1610, are Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the solar system, with hundreds of volcanoes erupting constantly, spewing sulfur and sulfur dioxide across its colorful surface. Europa is covered in a thick shell of water ice that likely conceals a global ocean of liquid water beneath. Where there's liquid water and energy, there could potentially be life, making Europa one of the most intriguing targets in the search for life beyond Earth. Ganymede is the largest moon in the solar system, even bigger than Mercury, and the only moon known to have its own magnetic field. Callisto is heavily cratered, its ancient surface preserving a record of impacts stretching back billions of years. Saturn, the sixth planet, is perhaps the most visually stunning world in our solar system thanks to its magnificent ring system. Like Jupiter, Saturn is a gas giant composed mainly of hydrogen and helium. It's the second largest planet, but has the lowest density of any planet. If you could find an ocean big enough, Saturn would float. The rings are made of countless chunks of water ice, ranging from tiny grains to house-sized boulders, all orbiting Saturn in a vast, thin disk. The rings are surprisingly thin, typically only 10 to 100 meters thick, despite spanning hundreds of thousands of kilometers across. Saturn has at least 146 known moons, more than any other planet. Titan, the largest, is bigger than Mercury and the only moon in the solar system with a thick atmosphere. Titan's atmosphere is mostly nitrogen with a small amount of methane, and its surface has lakes and seas of liquid methane and ethane. This is the only place besides Earth where we've confirmed the presence of stable liquid on a world's surface. Another moon, Enceladus, is covered in clean water ice and has geysers erupting from its south polar region, shooting water vapor and ice particles into space. Like Europa, Enceladus likely has a subsurface ocean and could potentially harbor life. Uranus, the seventh planet, rolls through space on its side with an axial tilt of about 98 degrees. This extreme tilt means Uranus's poles point almost directly at the Sun at different times during its 84-year orbit, creating the most extreme seasons in the solar system. Each pole gets 42 years of continuous sunlight, followed by 42 years of darkness. Uranus is an ice giant rather than a gas giant, with a composition dominated by water, methane, and ammonia ices rather than hydrogen and helium. The methane in its upper atmosphere absorbs red light, giving Uranus its distinctive cyan color. The planet has a faint ring system and at least 28 known moons. Neptune, the outermost planet, is similar to Uranus in size and composition, but has a vivid blue color and much more dramatic weather despite receiving far less energy from the Sun. Neptune has the strongest winds in the solar system, with speeds exceeding 2,000 kilometers per hour. The source of this energy is mysterious, as Neptune radiates more energy than it receives from the Sun. Like the other giant planets, Neptune has rings and moons. Triton, the largest moon, is unusual because it orbits Neptune backward in a retrograde direction. Astronomers think Triton was originally a dwarf planet from the Kuiper Belt that wandered too close to Neptune and was captured by the giant planet's gravity. Beyond Neptune's orbit lies the Kuiper Belt, a region of icy bodies similar to the asteroid belt but much larger and more massive. Pluto, once considered the ninth planet but now classified as a dwarf planet, is the best-known Kuiper Belt object. Pluto has 5 known moons, including Charon, which is large enough that Pluto and Charon orbit a common center of mass outside Pluto itself, making them almost a double dwarf planet system. Thousands of other icy worlds orbit in the Kuiper Belt, representing the frozen remnants of the early solar system. Even farther out, beginning at roughly 2,000 astronomical units from the Sun and extending to perhaps 100,000 astronomical units, is the hypothetical Oort cloud, a vast spherical shell of icy bodies surrounding the solar system. We've never directly observed the Oort cloud, but its existence is inferred from the orbits of long-period comets that occasionally fall into the inner solar system. These comets may have been knocked out of the Oort cloud by passing stars or tidal forces from the galaxy itself. The edge of the solar system is defined not by the orbit of any planet, but by the reach of the Sun's influence. At about 18 billion kilometers from the Sun, the solar wind, a constant stream of charged particles flowing outward from the Sun meets the interstellar medium and creates a boundary region called the heliopause. The Voyager 1 spacecraft, launched in 1977, crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Yet even Voyager 1, traveling at about 61,000 kilometers per hour, is still within the gravitational influence of the Sun and will be for thousands of years. Our solar system is our cosmic home, but it's just one of what we now know are billions of planetary systems in our galaxy alone. As we journey outward from the Sun, we leave behind this familiar realm and venture into the vast spaces between stars. The space between our Sun and the nearest stars is almost incomprehensibly vast. The nearest star system to our Sun is Alpha Centauri, actually a triple star system including Proxima Centauri, located about 4.2 light-years away. Remember, a light-year is the distance light travels in 1 year. Voyager 1, the fastest human-made object to leave the solar system, would take more than 70,000 years to reach Proxima Centauri at its current speed. Stars are the fundamental building blocks of the visible universe. They generate light and heat through nuclear fusion, forge the heavy elements in their cores, and through supernova explosions and their gravity organizes matter on cosmic scales. Without stars, the universe would be a dark and sterile place. Understanding stars means understanding how the universe creates complexity from simplicity, how atoms of hydrogen and helium become everything else, and ultimately, how we came to exist. Stars are born in nebulae, vast clouds of gas and dust drifting through interstellar space. These clouds can be enormous, spanning hundreds of light years across and containing enough material to form thousands of stars. Most of this material is hydrogen, the simplest and most abundant element in the universe, mixed with helium and trace amounts of heavier elements created in previous generations of stars. The gas in these clouds is extremely diffuse, with densities of about 100 to 1 million particles per cubic centimeter. For comparison, the air you're breathing contains about 25 quintillion molecules per cubic centimeter. Something must disturb these clouds to trigger star formation. A shock wave from a nearby supernova explosion can do it, or the tidal forces created when galaxies collide, or the pressure wave from a spiral arm passing through the region. Once a region of the cloud begins to collapse, gravity takes over. As the cloud contracts, it fragments into smaller clumps, each collapsing independently. These collapsing clumps are called protostars. As material falls inward, gravitational potential energy converts to heat, and the temperature at the center rises. When the core temperature reaches about 10 million degrees Celsius, hydrogen nuclei overcome their electric repulsion and fuse to form helium, releasing enormous amounts of energy in the process. A star is born. The outward pressure from this fusion energy balances the inward pull of gravity, and the star reaches a stable state. This is the main sequence phase, and stars spend most of their lives in this state, steadily fusing hydrogen into helium in their cores. Our Sun has been on the main sequence for about 4.6 billion years and has roughly another 5 billion years to go. Stars come in a wide range of masses, from less than a tenth the mass of our Sun to more than 100 times the Sun's mass. Mass determines almost everything about a star: its temperature, color, brightness, size, and how long it will live. The most massive stars burn through their hydrogen fuel at prodigious rates, shining with the light of millions of suns, but living only a few million years. The least massive stars, red dwarfs, burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. No red dwarf has ever died of old age because the universe isn't old enough yet. Astronomers classify stars by their surface temperature, which correlates with their color. The hottest stars, with surface temperatures above 30,000 degrees Celsius, glow blue or blue-white. These O-type and B-type stars are rare and massive. Our Sun is a G-type star with a surface temperature of about 5,500 degrees Celsius, giving it a yellow-white appearance. Cooler stars appear orange or red. The coolest M-type stars, the red dwarfs, have surface temperatures as low as 2,500 degrees Celsius. Stars exist in a delicate balance between gravity, trying to crush them, and thermal pressure from fusion, trying to blow them apart. This balance doesn't last forever. As a star ages and converts more hydrogen into helium in its core, the core's composition changes. Eventually, hydrogen fusion in the core slows and then stops. What happens next depends on the star's mass. For stars like our Sun, with masses between about 1/2 and 8 times the Sun's mass, the story continues like this. When hydrogen fusion in the core ceases, the core begins to contract under gravity. This contraction heats the core even more, and hydrogen fusion begins in a shell around the helium core. The energy from this shell burning pushes the outer layers of the star outward. The star swells to enormous size, its surface cooling as it expands. The star has become a red giant. In about 5 billion years, our Sun will enter its red giant phase. It will expand to roughly 200 times its current radius, engulfing the orbit of Mercury and likely Venus as well. Earth might survive as a scorched cinder at the outer edge of the expanded Sun, or it might be consumed entirely. Life on Earth will have ended long before this, as the gradually brightening Sun makes our planet uninhabitable in perhaps 1 billion years. Inside the red giant's core, helium accumulates under increasing pressure and temperature. When the core reaches about 100 million degrees Celsius, helium fusion ignites in a dramatic event called a helium flash. 3 helium nuclei fuse to form carbon, and this process also produces oxygen. The helium flash causes the core to expand, which lowers the temperature and reduces the total energy output. The star actually becomes smaller and dimmer after the helium flash, settling into a new stable state, fusing helium in its core and hydrogen in a shell. This helium burning phase lasts much shorter than the main sequence phase, perhaps 100 million years for a sun-like star. When the helium in the core is exhausted, the core again contracts. Helium begins fusing in a shell around a now carbon-oxygen core, and the outer layers expand again. The star has become an asymptotic giant branch star, larger and more luminous than before. But the core of a sun-mass star can never get hot enough to fuse carbon. The star becomes unstable, pulsating and shedding its outer layers in successive shells of gas. These expanding shells, illuminated by ultraviolet light from the exposed hot core, create what we call a planetary nebula, despite having nothing to do with planets. The name comes from their appearance through early telescopes, which made them look somewhat like planetary disks. The core left behind is called a white dwarf. This is one of the strangest objects in the universe. A white dwarf is typically about the size of Earth, but contains about half the mass of the Sun. The matter in a white dwarf is compressed to extraordinary densities, about 1 million times denser than water. A teaspoon of white dwarf material would weigh about 15 tons. The atoms are squeezed so tightly that electrons are pressed together into a degenerate state, where quantum mechanical principles prevent further collapse. The white dwarf shines not from fusion, which has ceased, but from residual heat. Over billions of years, it will slowly cool and fade, eventually becoming a black dwarf, though the universe isn't old enough for any white dwarfs to have cooled completely yet. For more massive stars, those with more than 8 times the Sun's mass, the ending is far more dramatic. These stars can fuse progressively heavier elements in their cores. After hydrogen comes helium, then carbon, neon, oxygen, and silicon, each stage producing the next heavier element and releasing energy. This progression forms a layered structure in the star's core, like an onion, with the heaviest elements at the center and lighter ones in shells around it. The final product of this fusion chain is iron. Iron is special. Fusing elements lighter than iron releases energy, but fusing iron consumes energy. When the core becomes pure iron, fusion stops. With no outward pressure to balance gravity, the core catastrophically collapses in less than a second. The iron core, roughly the size of Earth but with more mass than the Sun, compresses until atomic nuclei and electrons are forced together, forming a neutron star barely 20 kilometers across. The collapse releases an enormous amount of energy, most of it in the form of neutrinos, but enough remaining to blow apart the star's outer layers in a supernova explosion. For a few weeks, a supernova can outshine an entire galaxy, briefly shining with the light of billions of stars. These explosions enrich the interstellar medium with heavy elements created during the star's lifetime and in the explosion itself. Elements heavier than iron, including gold, platinum, and uranium, are primarily created in supernova explosions, and even more dramatically in colliding neutron stars. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged in the core of a star and scattered into space when that star died. We are, quite literally, made of stardust. What remains after the supernova depends on the mass of the original core. If the core was between roughly 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These objects are extraordinarily dense, with the mass of the Sun compressed into a sphere the size of a city. Neutron stars spin rapidly, often many times per second, and have incredibly strong magnetic fields. Some neutron stars emit beams of radiation from their magnetic poles that sweep past Earth like lighthouse beams as the star rotates. These are called pulsars, and they were first discovered in 1967, initially mistaken for signals from an alien civilization before their true nature was understood. If the collapsing core exceeds about 3 times the Sun's mass, not even neutron degeneracy pressure can halt the collapse. The core continues contracting, becoming infinitely dense at a single point called a singularity. This is a black hole, and we'll discuss these remarkable objects in detail next. Black holes represent the most extreme objects in the known universe, places where gravity becomes so powerful that not even light can escape. The boundary around a black hole from which escape becomes impossible is called the event horizon. Cross that boundary, and you're gone forever, falling inexorably toward the central singularity. Nothing that falls into a black hole can ever escape or communicate with the outside universe. In a very real sense, what happens inside a black hole is removed from our universe entirely. The concept of a black hole emerges from Einstein's general theory of relativity, which describes gravity not as a force, but as curvature in the fabric of space-time. Massive objects curve space-time around them, and this curvature determines how other objects move. The stronger the gravity, the more extreme the curvature. At the event horizon of a black hole, space-time curvature becomes infinite, creating a one-way barrier. Time itself behaves strangely near black holes. To an outside observer, an object falling toward a black hole appears to slow down as it approaches the event horizon, its light redshifting and dimming until it seems to freeze forever just at the edge. But from the perspective of the falling object, nothing special happens at the event horizon. It simply crosses over and continues falling. Astronomers categorize black holes by their mass. Stellar mass black holes form from the collapse of massive stars, as we discussed. These typically have masses between about 5 and several tens of times the mass of the Sun. The Milky Way galaxy likely contains tens of millions to 100 million stellar mass black holes, though they're incredibly difficult to detect. We can only find them when they're part of a binary system with a normal star. Material pulled from the companion star spirals down toward the black hole, forming an accretion disk. Friction in the disk heats the material to millions of degrees, causing it to emit intense X-rays before plunging through the event horizon. Supermassive black holes are millions to billions of times more massive than the Sun. Almost every large galaxy, including our Milky Way, has a supermassive black hole at its center. Our galaxy's supermassive black hole, called Sagittarius A star, has a mass of about 4 million suns. Despite this enormous mass, it's relatively quiet compared to black holes in other galaxies. Sagittarius A star rarely feeds, only occasionally swallowing stray gas clouds or stars that wander too close. Other supermassive black holes are far more active. When material falls toward them at high rates, they become active galactic nuclei, among the most luminous objects in the universe. The accretion disk around an active supermassive black hole can outshine all the stars in its host galaxy combined. Some active galactic nuclei launch jets of material at nearly the speed of light, perpendicular to the accretion disk. These jets can extend for hundreds of thousands of light years into space, energizing vast regions of the intergalactic medium. The most powerful jets contain more energy than has been released by all the stars in their host galaxies over their entire lifetimes. How supermassive black holes form remains one of the biggest mysteries in astrophysics. They're too massive to have formed from a single star's collapse, and we observe supermassive black holes in galaxies that existed less than 1 billion years after the Big Bang. There simply wasn't enough time for them to grow from stellar mass black holes by accumulating matter. Several formation mechanisms have been proposed. Perhaps they formed from the direct collapse of massive gas clouds in the early universe. Perhaps they grew through mergers of many smaller black holes. Perhaps they formed from massive stars that existed in the early universe when conditions were very different from today. We're still working to understand their origins. Between stellar mass and supermassive black holes should theoretically be intermediate mass black holes, weighing in at hundreds to hundreds of thousands of times the Sun's mass. These are surprisingly rare, or at least rarely detected. A few candidates have been found, usually in the dense centers of globular star clusters or as wandering objects between galaxies. Why these intermediate mass black holes are so uncommon is another puzzle. The physics near black holes becomes increasingly strange as you approach the event horizon. Tidal forces, the difference in gravitational pull between your head and feet, become extreme. For a stellar mass black hole, These tidal forces would tear you apart long before you reach the event horizon, stretching you like taffy in a process astronomers grimly call spaghettification. For a supermassive black hole, the tidal forces at the event horizon are much weaker because the event horizon is much farther from the singularity. You could cross the event horizon of a supermassive black hole and feel nothing unusual, at least initially, though you'd have no way to turn back and no way to survive the eventual encounter with the singularity. Black holes are not the cosmic vacuum cleaners sometimes portrayed in popular culture. They don't reach out and suck in everything around them. Their gravity, while extreme at close range, falls off with distance just like any other object's gravity. If our sun was suddenly replaced with a black hole of equal mass, Earth's orbit wouldn't change. We'd freeze in the darkness, but we wouldn't be pulled into the black hole. You have to get very close to a black hole for its gravity to be noticeably different from that of a normal object with the same mass. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's event horizon, or more precisely, the shadow of the event horizon surrounded by the glowing accretion disk. The black hole, at the center of the galaxy M87, is about 6.5 billion times more massive than the Sun and located about 55 million light-years from Earth. The image shows exactly what relativity predicts: a dark, central region surrounded by a ring of light bent by the black hole's gravity. In 2022, they released a similar image of Sagittarius A star, our galaxy's own supermassive black hole. These images represent an extraordinary achievement, requiring the coordination of radio telescopes around the world to create an Earth-sized virtual telescope. Black holes also emit Hawking radiation, a quantum mechanical effect predicted by physicist Stephen Hawking in 1974. According to quantum mechanics, particle-antiparticle pairs constantly pop into existence throughout space, usually annihilating each other almost instantly. Near a black hole's event horizon, one particle of the pair might fall into the black hole while the other escapes. To an outside observer, it appears the black hole has emitted a particle. This process causes black holes to slowly evaporate over time, though the timescales are enormous. A black hole with the mass of the Sun would take about 10 to the 67th years to evaporate completely, far longer than the current age of the universe. Smaller black holes evaporate faster than large ones. In the final moments of a black hole's life, it would evaporate catastrophically in a burst of radiation. However, no black holes are currently old enough or small enough to be near this stage. In fact, most black holes are actually growing, accumulating matter faster than they lose mass, through Hawking radiation. Black holes connect to some of the deepest questions in physics. What happens to information that falls into a black hole? Does it truly disappear, violating quantum mechanics, or is it somehow preserved? This is the black hole information paradox, and physicists have been debating it for decades. How do we reconcile general relativity, which describes gravity and space-time curvature, with quantum mechanics, which governs the behavior of particles and energy? We need a theory of quantum gravity to fully understand black holes, and developing such a theory remains one of the central challenges in theoretical physics. Black holes are not just cosmic curiosities. They play important roles in galaxy formation and evolution. The supermassive black holes at galaxy centers can regulate star formation across their entire galaxies. When they're actively feeding and driving powerful jets, they can heat the surrounding gas and prevent it from cooling and forming stars. The relationship between supermassive black holes and their host galaxies is surprisingly tight. There's a strong correlation between black hole mass and the properties of the galaxy's central bulge, suggesting they evolved together. As we journey through the galaxy, we encounter regions of space that glow with ethereal beauty, vast clouds of gas and dust illuminated in stunning colors. These are nebulae, from the Latin word for cloud. Nebulae are the birthplaces and graves of stars, cosmic recycling centers where the material of dead stars returns to the interstellar medium to eventually form new generations of stars and planets. Emission nebulae glow with their own light, excited by radiation from hot, young stars embedded within them. The most famous example is the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword. The Orion Nebula is a stellar nursery, a place where stars are actively forming right now. It lies about 1,350 light-years from Earth and spans roughly 24 light-years across. Within the nebula, we can see protostars in various stages of formation, surrounded by protoplanetary disks where planets are beginning to form. The characteristic reddish-pink color of many emission nebulae comes from hydrogen gas. When ultraviolet light from hot stars strikes hydrogen atoms, it strips away the electrons, ionizing the gas. When electrons recombine with hydrogen nuclei, they emit light at specific wavelengths, including a prominent red line called hydrogen alpha. Other elements contribute different colors. Oxygen produces greenish hues, while sulfur adds deeper red tones. The complex interplay of these emission lines creates the rich color palette we see in nebula images. Another stunning emission nebula is the Lagoon Nebula, about 4,000 light-years distant in the constellation Sagittarius. It spans about 110 light-years across and contains several young star clusters. Dark lanes of dust snake through the nebula, regions where the dust is so thick it blocks light from the glowing gas behind it. These dark regions often mark places where the densest gas is collapsing to form new stars. The Eagle Nebula, about 7,000 light-years away, contains the famous Pillars of Creation, towering columns of gas and dust sculpted by intense radiation from nearby stars. The pillars are each several light-years long, though they're being gradually eroded by the very radiation that makes them visible. Inside these pillars, new stars are forming, hidden from direct view by the surrounding dust. We see the Eagle Nebula as it was 7,000 years ago. For all we know, a nearby supernova may have already destroyed the Pillars of Creation, but the light showing us their destruction won't reach Earth for thousands of years more. Reflection. Nebulae don't emit their own light, but instead reflect light from nearby stars. They appear blue for the same reason Earth's sky appears blue. Small dust particles scatter blue light more efficiently than red light, so when starlight passes through or reflects off these dust clouds, the blue light is preferentially scattered toward us. The Pleiades star cluster, visible as a tight group of bright stars to the naked eye, is surrounded by a reflection nebula. The young, hot stars of the Pleiades are passing through a cloud of interstellar dust, and their light reflects off this dust, creating delicate blue wisps around the stars. Dark nebulae are dense clouds of dust that block light from stars or glowing gas behind them. They appear as dark patches against the brighter background of the Milky Way. The Coalsack Nebula in the southern hemisphere is a prominent example, appearing as a dark blot on the bright band of the Milky Way. The Horsehead Nebula in Orion is another famous dark nebula, appearing as a horse's head silhouetted against a background of glowing hydrogen gas. These dark nebulae are often cold, with temperatures only a few degrees above absolute zero, making them ideal locations for molecules to form. Many dark nebulae are molecular clouds, containing not just hydrogen atoms, but also molecules like carbon monoxide, water, ammonia, and even more complex organic compounds. Planetary nebulae, despite their misleading name, are shells of gas expelled by dying sun-like stars. When a red giant star sheds its outer layers, the exposed hot core emits intense ultraviolet radiation that ionizes and illuminates the expanding gas shell. The result is often a beautiful, symmetric structure with intricate details. The Ring Nebula in Lyra is a classic example, appearing through telescopes as a smoke ring in space. It's about 2,300 light-years away and roughly 1 light-year across. At its center is the white dwarf remnant of the star that created the nebula. The Cat's Eye Nebula is one of the most complex planetary nebulae known, with concentric rings, jets, and intricate structures that suggest the central star went through multiple episodes of mass loss. The Helix Nebula, often called the Eye of God, is one of the closest planetary nebulae at about 650 light-years away. It spans about 2.5 light-years across and shows remarkable detail in high-resolution images, including thousands of radial filaments extending outward from the central star. Supernova remnants are the expanding debris clouds from exploded stars. These are some of the most energetic phenomena in the galaxy, with the expanding shockwave from the supernova heating the surrounding gas to millions of degrees and emitting powerful X-rays. The Crab Nebula is the remnant of a supernova that was observed from Earth in 1054 CE. Chinese and Arab astronomers recorded seeing a new star in the sky bright enough to be visible during the day for several weeks. Today, the nebula spans about 11 light-years and is still expanding at about 1,500 kilometers per second. At its heart is a pulsar, a rapidly spinning neutron star that flashes 30 times per second, pumping energy into the nebula and creating intricate structures in the gas. The Cygnus Loop, also known as the Veil Nebula, is an older supernova remnant, between 10,000 and 20,000 years old. It spans about 3 degrees on the sky, roughly 6 times the diameter of the full moon, though it's much fainter. The expanding shockwave has swept up surrounding interstellar gas, creating delicate, lace-like structures visible in detailed images. Nebulae remind us that space is not empty. Between the stars lies a thin but pervasive medium of gas and dust, the raw material for future generations of stars and planets. The life cycle of matter in the universe flows through nebulae. Stars form from molecular clouds, live out their lives fusing hydrogen into heavier elements, then return much of that material to space through stellar winds and supernova explosions. This enriched material mixes with the interstellar medium, becomes part of new molecular clouds, and eventually forms new stars with higher metallicity, more heavy elements than previous generations. Our Sun and Solar System formed from a molecular cloud enriched by previous generations of stars. The heavy elements in Earth, in your body, all came from stars that lived and died before the Sun was born. We are connected to the cosmos through this great cycle of stellar birth, life, and death, played out in the glowing clouds we call nebulae. Zooming out from individual nebulae and stars, we now contemplate galaxies, vast gravitationally bound collections of stars, gas, dust, and dark matter. Our Milky Way galaxy is just one of hundreds of billions, perhaps trillions, of galaxies in the observable universe. Each galaxy contains millions, billions, or even trillions of stars. The distances between galaxies are so vast, they're measured in millions of light-years. Yet despite these enormous distances, galaxies are not isolated. They interact, merge, and organize themselves into larger structures that define the architecture of the cosmos. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend. The galaxy is roughly 100,000 light-years in diameter and contains an estimated 200 to 400 billion stars, along with vast amounts of gas, dust, and dark matter. Our solar system sits in a minor spiral arm called the Orion Spur, about 27,000 light-years from the galactic center. The disk of the Milky Way is relatively thin, only about 1,000 light-years thick in most places, embedded within a much larger spherical halo of older stars and globular clusters that extends perhaps 200,000 light-years from the center. The spiral arms of the Milky Way are not permanent structures, but density waves moving through the disk. Stars and gas clouds moving through the galaxy occasionally pass through these density waves, where they bunch up temporarily before moving on. The increased density in spiral arms triggers star formation, which is why spiral arms appear bright and blue in images of other galaxies. The young, hot blue stars formed in the arms are short-lived, dying before they can move far from where they formed, while older, dimmer stars fill in the space between arms. At the Milky Way's center, hidden behind thick clouds of dust from our perspective, but observable in infrared and radio wavelengths, lies the supermassive black hole Sagittarius A star. The stars closest to this black hole move at enormous speeds, orbiting it in just a few years. By tracking these stellar motions over decades, astronomers have precisely measured the black hole's mass at about 4 million solar masses. One star, designated S2, orbits Sagittarius A star in less than 16 years, reaching speeds up to about 5,000 kilometers per second at its closest approach. The Milky Way doesn't exist in isolation. It's the dominant member of the local group, a collection of more than 80 galaxies spread across about 10 million light-years. The Andromeda Galaxy, a larger spiral galaxy about 2.5 million light-years away, is the other major member of the local group. Andromeda contains roughly 1 trillion stars, about twice as many as the Milky Way, and spans about 220,000 light-years across. On a clear, dark night, Andromeda is visible to the naked eye as a faint, fuzzy patch, the most distant object readily visible without a telescope. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second. In about 4.5 billion years, they'll collide and begin merging. This might sound catastrophic, but galaxy collisions rarely involve actual stellar collisions. Stars are so far apart relative to their size that they pass by each other like gnats in 2 intersecting swarms. However, the gravitational interactions during the collision will dramatically rearrange both galaxies, triggering intense bursts of star formation and eventually creating a single elliptical galaxy that some astronomers have nicknamed Milkomeda. The local group contains several other notable galaxies. The large and small Magellanic Clouds, visible from the southern hemisphere, are irregular dwarf galaxies in orbit around the Milky Way. The Large Magellanic Cloud is about 160,000 light-years away and contains roughly 30 billion stars. It's a site of vigorous star formation, including the Tarantula Nebula, one of the most active star-forming regions known. The Triangulum Galaxy, a smaller spiral about 3 million light-years away, is the third largest member of the local group. Beyond the local group, galaxies come in several main types. Spiral galaxies, like the Milky Way and Andromeda, have flattened disks with spiral arm patterns and central bulges. They contain substantial amounts of gas and dust, ongoing star formation, and populations of young and old stars. Barred spiral galaxies have bar structures in their centers, while normal spirals don't. About 2/3 of spiral galaxies are barred. The bar structure may help funnel gas toward the galactic center, potentially feeding the central supermassive black hole or triggering central star formation. Elliptical galaxies range from nearly spherical to highly elongated shapes. They contain little gas or dust and show little or no ongoing star formation. Their stars are generally older and redder than those in spirals. Elliptical galaxies range from dwarf ellipticals, containing only a few million stars, to giant ellipticals with trillions of stars. The largest galaxies in the universe are giant ellipticals found at the centers of galaxy clusters, formed through repeated mergers of smaller galaxies over cosmic time. Irregular galaxies lack any clear structure or symmetry. Many are small and faint, but some, like the Magellanic Clouds, are quite substantial. Irregular galaxies often show active star formation and may result from gravitational interactions or mergers with other galaxies. The distorted shapes tell stories of cosmic violence and transformation. Lenticular galaxies are transitional between spirals and ellipticals. They have a disk and central bulge like spirals, but contain little gas or dust and show little star formation, like ellipticals. They're sometimes called armless spirals because they lack the bright spiral arm patterns. Galaxy morphology connects to evolutionary history. Elliptical galaxies typically form through mergers of smaller galaxies. The merger process scrambles the orbital patterns of stars, erasing the ordered disk structure and creating the more random distribution of stellar motions seen in ellipticals. Spiral galaxies have had quieter histories, accumulating gas over billions of years and maintaining their disk structures. The transformation from spiral to elliptical through mergers is a one-way process. Once a galaxy becomes elliptical, it cannot easily return to a spiral form. Many galaxies interact with their neighbors. Tidal forces during close encounters can draw out long streams of stars and gas, creating spectacular structures. The Antennae galaxies, about 45 million light-years away in the constellation Corvus, are 2 spiral galaxies in the process of colliding. Long tidal tails of stars extend from both galaxies, resembling an insect's antennae, hence the name. The collision has triggered intense star formation in the overlap region between the 2 galaxies. The Whirlpool Galaxy, M51, is a stunning face-on spiral about 23 million light-years away. Its prominent spiral arms are enhanced by gravitational interaction with a smaller companion galaxy. The companion has pulled material from the larger galaxy, stimulating star formation and making the spiral pattern particularly dramatic. Some galaxies form beautiful ring structures. Hoag's object is a nearly perfect ring galaxy, with a dense core of old yellow stars surrounded by a detached ring of young blue stars. The ring is about 120,000 light-years in diameter, and there's almost nothing visible between the core and the ring. The origin of ring galaxies like this remains debated, but they likely form when a smaller galaxy passes through the center of a larger disk galaxy, creating an expanding density wave that triggers star formation in a ring pattern. Active galaxies host supermassive black holes that are actively feeding on large amounts of material. These are the most luminous objects in the universe. Quasars, the most luminous type of active galaxy, can shine with the light of 100 trillion stars from a region smaller than our solar system. The term quasar is short for quasi-stellar radio source because the first ones discovered appeared almost star-like in optical images despite being billions of light-years away. We now know they're the extremely luminous cores of distant galaxies, powered by supermassive black holes consuming matter at prodigious rates. The most distant known quasars existed when the universe was less than 1 billion years old, showing that supermassive black holes formed very early in cosmic history. These distant quasars are so far away that their light has been traveling toward us for more than 13 billion years. We see them as they were in the universe's infancy, giving us a window into cosmic conditions very different from today. Radio galaxies emit enormous amounts of energy at radio wavelengths, often displaying jets of particles streaming away from the central black hole at nearly the speed of light. These jets can extend for millions of light-years, far beyond the visible galaxy. Centaurus A, one of the nearest radio galaxies at about 12 million light-years away, shows jets extending roughly 1 million light-years into space. The galaxy itself is peculiar, an elliptical galaxy with a prominent dust lane across its center, likely the result of a merger with a spiral galaxy. Galaxies are not randomly distributed through space. They cluster together in groups and larger clusters, which in turn organize into even larger structures called superclusters. The Virgo cluster, about 65 million light-years away, contains roughly 2,000 galaxies. The Coma cluster, about 300 million light-years distant, contains thousands of galaxies packed into a region about 20 million light-years across. The galaxies in rich clusters move at speeds of hundreds or thousands of kilometers per second, bound together by their mutual gravity. The discovery that galaxies cluster led to one of the most important findings in cosmology. In the 1930s, Fritz Zwicky studied the Coma cluster and measured how fast its galaxies were moving. He found they were moving so fast that the cluster's visible mass couldn't possibly hold it together gravitationally. The galaxies should have escaped long ago. Zwicky concluded that the cluster must contain large amounts of unseen matter, which he called dark matter. We'll explore this mysterious component of the universe in detail later. Galaxy clusters themselves organize into superclusters, structures extending across hundreds of millions of light-years. Our local group is part of the Virgo supercluster, which contains roughly 100 galaxy groups and clusters and spans about 110 million light-years. The Virgo cluster sits near the center, with the local group positioned toward the outer edge. Recent mapping efforts have revealed an even larger structure, the Laniakea supercluster, of which the Virgo supercluster is just one part. Laniakea spans about 500 million light-years and contains roughly 100,000 galaxies. The name Laniakea means immeasurable heaven in Hawaiian, a fitting description for a structure of such enormous scale. We're not just members of the local group or the Virgo supercluster. Our cosmic address extends to the Laniakea supercluster, and beyond that, to the even larger scale structure of the cosmic web. For most of human history, the only planets we knew were those in our own solar system. Philosophers and scientists speculated about planets orbiting other stars, but without any way to detect them, these worlds remained purely hypothetical. That changed in the 1990s when astronomers developed techniques sensitive enough to detect planets around other stars. Today, we know of more than 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. These discoveries have revolutionized our understanding of planetary systems and raised profound questions about the possibility of life beyond Earth. Detecting exoplanets is extremely challenging. Even the largest planet appears tiny next to its parent star and emits no light of its own, only reflected starlight. A Jupiter-sized planet orbiting a Sun-like star would appear about 1 billion times fainter than the star and separated by an angle of about 1 arc-second at a distance of 5 light-years. That's like trying to see a firefly next to a searchlight from thousands of kilometers away. The first confirmed exoplanet orbiting a Sun-like star was discovered in 1995 by Swiss astronomers Michel Mayor and Didier Queloz, who shared the 2019 Nobel Prize in Physics for this achievement. The planet, called 51 Pegasi b, shocked everyone because it was a Jupiter-mass planet orbiting extremely close to its star, completing an orbit in just 4 days. Conventional theories of planetary system formation, based on our solar system, predicted that giant planets should form far from their stars, where temperatures are cold enough for ice to form. This hot Jupiter, as such planets came to be called, suggested that planets could migrate inward after forming, dramatically changing their orbits over time. The radial velocity method, used to discover 51 Pegasi b, works by detecting the wobble a planet's gravity induces in its parent star. As the planet orbits, its gravitational pull causes the star to move in a small orbit around the system's center of mass. When the star moves toward us, its light is slightly blue-shifted to shorter wavelengths. When it moves away, the light is slightly red-shifted. By measuring these tiny shifts in the star's spectrum, astronomers can infer the presence of orbiting planets. The technique is most sensitive to large planets in close orbits, which create the largest stellar wobbles. The transit method detects planets that pass directly in front of their stars from our perspective, causing a tiny periodic dimming. When a planet transits its star, it blocks a small fraction of the star's light. For an Earth-sized planet transiting a Sun-like star, the dimming is less than 1% and lasts only a few hours. For a Jupiter-sized planet, the dimming can reach 1 to 2%. By measuring a star's brightness precisely over time, astronomers can detect these periodic dips and infer the presence of planets. The transit method provides information about a planet's size, orbital period, and if we're very lucky, something about its atmosphere. NASA's Kepler Space Telescope, launched in 2009, used the transit method to revolutionize exoplanet science. Kepler stared at a single patch of sky containing about 150,000 stars, monitoring their brightness continuously for over 4 years. The mission discovered more than 2,700 confirmed exoplanets and thousands of additional candidates. Kepler revealed that planets are incredibly common, with most stars hosting at least one planet. Statistically, there are likely more planets than stars in the Milky Way galaxy. Though, Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, continues the search for exoplanets, surveying the entire sky rather than focusing on one region. TESS has discovered thousands of exoplanet candidates, many around bright, nearby stars that are ideal targets for follow-up observations with more powerful telescopes. Exoplanets come in an astonishing variety. Hot Jupiters are gas giant planets orbiting very close to their stars, with surface temperatures reaching thousands of degrees. Their atmospheres are likely being stripped away by the intense stellar radiation. Some hot Jupiters are tidally locked, always showing the same face to their stars, creating extreme temperature differences between day and night sides. Super-Earths are planets with masses between Earth's and Neptune's, a size category absent from our solar system. They're the most common type of exoplanet discovered. Some super-Earths may be rocky worlds with thick atmospheres, while others might be mini-Neptunes with hydrogen-helium envelopes. We don't yet know which category most super-Earths fall into. Mini-Neptunes are intermediate in size between Earth and Neptune, with thick hydrogen-helium atmospheres, but rocky or icy cores. Many exoplanets discovered by Kepler fall into this category. Some mini-Neptunes orbit in their star's habitable zones, the region where surface temperatures might allow liquid water. However, Planets with thick hydrogen atmospheres are unlikely to host life as we know it, even if they're in the habitable zone. Water worlds are a hypothetical type of planet with deep global oceans covering the entire surface. While Earth has oceans, they're relatively shallow compared to the planet's radius. A true water world might have oceans hundreds or thousands of kilometers deep, with exotic forms of high-pressure ice at the bottom rather than a rocky surface. Some exoplanets have densities suggesting they could be water worlds, but we don't yet have definitive confirmation. Terrestrial exoplanets similar in size to Earth are particularly interesting in the search for life. Earth-mass planets in their stars' habitable zones are prime candidates for hosting liquid water on their surfaces. The TRAPPIST-1 system, 39 light-years from Earth, contains 7 Earth-sized planets orbiting a small, cool red dwarf star. 3 of these planets orbit in the habitable zone. The system is packed tightly together, with all 7 planets orbiting closer to their star than Mercury orbits our Sun. Because the star is so cool and dim, this close orbit still allows temperatures compatible with liquid water. Proxima Centauri b, orbiting the nearest star to our Sun, is slightly more massive than Earth and orbits in the habitable zone of its red dwarf star. However, red dwarf stars frequently emit powerful flares that could strip away planetary atmospheres, potentially making them inhospitable for life despite being in the habitable zone. Whether red dwarf planets can maintain thick atmospheres and stable surface conditions remains an open question. The James Webb Space Telescope, launched in 2021, is beginning to analyze exoplanet atmospheres in unprecedented detail. By observing planets as they transit their stars, JWST can detect which wavelengths of starlight are absorbed by the planetary atmosphere, revealing the presence of different molecules. So far, JWST has detected water vapor, carbon dioxide, sulfur dioxide, and other molecules in several exoplanet atmospheres. Future observations might detect biosignature gases, molecules that could indicate the presence of life, such as oxygen, methane, or more exotic compounds. Finding life on an exoplanet would be one of the most profound discoveries in human history. It would answer the ancient question of whether we're alone in the universe. If we find that life arose independently on another world, it would suggest that life is common throughout the universe wherever conditions are suitable. If we search many worlds and find no evidence of life, it might suggest that life is extremely rare, or that we're the only technological civilization in our cosmic neighborhood. The existence of thousands of exoplanets hints at the enormous diversity of worlds in the universe. Every star we see in the night sky likely has planets. Some of those planets might have moons. Some might harbor oceans. Some might have atmospheres with weather, clouds, and rain. And on some fraction of these worlds, perhaps life has arisen. We're only beginning to explore this vast population of other worlds. Stepping back from individual galaxies and even galaxy clusters, we can see that the universe has structure on the largest scales. If you could map the positions of millions of galaxies across billions of light years, you discover they're not randomly distributed. Instead, they form a vast cosmic web, a network of filaments and sheets surrounding enormous empty voids. This structure, the largest we know of in the universe, emerged from tiny quantum fluctuations in the early universe and grew under the influence of gravity over billions of years. Galaxy surveys have mapped millions of galaxies in 3 dimensions, determining not just their positions on the sky, but also their distances from Earth. These surveys reveal the cosmic web structure clearly. Galaxies cluster along dense filaments, like beads on strings, with clusters forming at the intersections of multiple filaments. Between the filaments lie vast voids, regions containing very few galaxies. The largest voids span hundreds of millions of light years across and are nearly empty of galaxies, though they're not completely empty. They still contain some matter, just at much lower density than the cosmic average. The filaments and walls of the cosmic web contain most of the universe's galaxies. Our local group sits on a filament, as do most galaxies. The densest regions, where filaments intersect, host galaxy clusters and superclusters. The Virgo cluster sits at a major node in our region of the cosmic web, and the entire Laniakea supercluster represents a large-scale concentration of matter along connected filaments. This structure formed through gravitational instability. The early universe was remarkably smooth, with density varying from place to place by only about 1 part in 100,000. But even these tiny variations were enough. Regions that were slightly denser had slightly stronger gravity, attracting more matter from their surroundings. This made them even denser, strengthening their gravity further. Over hundreds of millions of years, this process amplified the initial tiny fluctuations into the large-scale structure we see today. The process happened hierarchically. Small density fluctuations collapsed first, forming the first stars and small galaxies. These merged to form larger galaxies. Galaxies clustered into groups and clusters organized into superclusters. The structure grew from the bottom up, with smaller structures merging to form larger ones, a process that continues today. Computer simulations can model this process, starting from the initial conditions of the early universe and evolving the distribution of matter forward in time under gravity. The results match observations remarkably well, producing cosmic web structures very similar to what we see in galaxy surveys. The cosmic web isn't static. It's constantly evolving as matter flows along filaments toward dense regions. Galaxies fall into clusters. Clusters merge to form larger clusters. The universe on these scales is dynamic, though the timescales are so long that we don't see much change in a human lifetime or even over the history of astronomy. The largest single structures known are supervoids and superclusters. The Sloan Great Wall is a cosmic filament about 1.37 billion light-years long, containing tens of thousands of galaxies. It's one of the largest coherent structures known. The Eridanus supervoid is an enormous underdense region, about 1 billion light-years across, containing far fewer galaxies than average. These structures are so large they're comparable to a significant fraction of the observable universe's size, approaching the limit of how large structures can be given the universe's age and the speed of light. The cosmic web is dominated by dark matter. The luminous matter we can see, stars and gas, traces out the web's structure, but dark matter provides most of the gravitational force that forms and maintains this structure. Simulations of structure formation that include only normal matter don't produce structures matching observations. When dark matter is included, the simulations match reality beautifully. The dark matter forms its own web structure, and galaxies form where the dark matter is densest. Between the filaments of the cosmic web lies the intergalactic, medium, gas that never fell into galaxies. This gas is extremely diffuse, typically only about 1 particle per cubic meter, much more diffuse than the best vacuum we can create on Earth. Despite its low density, there's so much space between galaxies that the intergalactic medium contains more baryonic matter than all the stars and gas in galaxies combined. Most of this gas is hydrogen and helium, heated to temperatures of thousands to millions of degrees by gravitational collapse, shocks, and radiation from galaxies. In the densest regions, around galaxy clusters, the intergalactic medium reaches temperatures of tens of millions of degrees and emits powerful X-rays. These hot intracluster gas halos can contain more baryonic matter than all the stars in the cluster's galaxies. The gas between galaxies is invisible at optical wavelengths, but reveals itself through its absorption of light from distant quasars and its emission of X-rays. The cosmic web represents the outcome of 14 billion years of cosmic evolution. The universe began in an extremely smooth, nearly uniform state and evolved into the rich, structured cosmos we see today. Understanding how this structure formed and evolved helps us understand the universe's history, its composition, and its future. The cosmic web is not just a pattern in the distribution of galaxies. It's a record of how the universe has grown and changed since the Big Bang. The universe we can see, the stars, planets, nebulae, galaxies, everything that emits or absorbs light, accounts for less than 5% of the total mass energy of the universe. The rest, 95%, is invisible to our telescopes and made of things we don't fully understand. About 27% is dark matter, an unknown form of matter that interacts through gravity but not through electromagnetism. About 68% is dark energy, an even more mysterious form of energy causing the universe's expansion to accelerate. These dark components dominate the universe, shaping its structure and determining its fate, yet we don't know what they are. Evidence for dark matter comes from multiple independent observations. The first hint came from Fritz Zwicky's study of the Coma cluster in the 1930s. By measuring how fast galaxies moved within the cluster, he could estimate the cluster's total mass using Newton's laws. He found the cluster needed to be about 400 times more massive than the visible matter alone to keep the galaxies bound. Zwicky proposed the existence of unseen matter, though his ideas weren't widely accepted at the time. In the 1970s, Vera Rubin and Kent Ford studied rotation curves of spiral galaxies. They measured how fast stars and gas orbit at different distances from galaxy centers. Newton's laws predict that orbital speed should decrease with distance from the center, just as planets farther from the Sun orbit more slowly. But Rubin and Ford found that rotation speeds remained roughly constant even in the outer parts of galaxies, far beyond where most visible matter ends. The only way to explain this was if galaxies were embedded in massive halos of invisible matter extending far beyond the visible disk. This dark matter provides the extra gravity needed to keep the outer parts of galaxies rotating as fast as they do. Gravitational lensing provides another powerful probe of dark matter. Einstein's general relativity predicts that massive objects curve spacetime, bending the path of light passing nearby. When light from a distant galaxy passes near a massive galaxy cluster, the cluster's gravity acts like a lens, bending and distorting the background galaxy's image. By measuring this distortion, astronomers can map the cluster's total mass distribution, including dark matter. The Bullet cluster provides particularly dramatic evidence for dark matter. This is actually two galaxy clusters that collided and passed through each other. When this happened, the hot X-ray emitting gas in both clusters interacted and slowed down, remaining near the collision site. But the galaxies, being small compared to the space between them, mostly passed through without collision. Gravitational lensing maps show that most of the mass passed through with the galaxies, not staying with the gas. This mass can't be the galaxies themselves. They don't contain enough visible matter. It must be dark matter halos surrounding each cluster, which pass through each other just as the galaxies did. The Bullet cluster shows dark matter and normal matter spatially separated, powerful evidence that dark matter is a real substance, not just a modification to the laws of gravity. The cosmic microwave background also provides evidence for dark matter. The patterns of temperature fluctuations in the CMB depend on the amount and types of matter present in the early universe. Observations match predictions only if about 85% of the matter in the universe is dark matter, with the remaining 15% being ordinary atoms. So, what is dark matter? We don't know for certain, but we have candidates. The leading possibility is that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would interact only through gravity and the weak nuclear force, making them extremely difficult to detect. They'd pass through ordinary matter almost without interaction. Hundreds of experiments around the world are searching for WIMPs, typically using large tanks of ultra-pure materials deep underground to shield them from cosmic rays. So far, no convincing WIMP detections have been confirmed. Another possibility is axions, hypothetical particles much lighter than WIMPs. Axions were originally proposed to solve a problem in particle physics, but could also be dark matter. Several experiments are searching for axions with so far no confirmed detections. Primordial black holes formed in the early universe might contribute to dark matter, though observations suggest they can't account for all of it. Various exotic particles predicted by theoretical physics beyond the standard model could also be dark matter. The truth is, we're searching somewhat in the dark, excuse the pun, because we don't know what we're looking for. Dark matter doesn't just exist. It plays a crucial role in structure formation. Without dark matter, galaxies and galaxy clusters couldn't have formed. The universe would look completely different, and we probably wouldn't exist. Dark matter provides the gravitational framework on which normal matter assembles. Dark matter collapsed into halos first, creating gravitational potential wells into which gas could fall. This gas eventually formed stars and galaxies. Every galaxy sits in a dark matter halo much more massive and extended than the visible galaxy itself. Dark energy is even more mysterious than dark matter. The evidence for dark energy comes from observations of distant supernovae. In the 1990s, two teams independently studied type Ia supernovae, which are excellent standard candles because they all reach roughly the same peak brightness. By measuring how bright these supernovae appear from Earth and comparing to their known intrinsic brightness, astronomers can determine their distances. By measuring the redshift of their host galaxies, astronomers can determine how fast they're receding. Both teams expected to find that the universe's expansion was slowing down due to gravity. Instead, they discovered the expansion is speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than expected, meaning the universe has expanded more than it would have if expansion was slowing down. This accelerated expansion requires a repulsive force counteracting gravity on cosmic scales. This force is what we call dark energy. Dark energy appears to be a property of space itself. As the universe expands and creates more space, there's more dark energy. The density of dark energy remains constant even as the universe expands, unlike matter density, which decreases as the universe grows. This is very strange behavior. It's as if the vacuum of space has energy, and this energy has negative pressure that pushes space apart. The simplest explanation for dark energy is Einstein's cosmological constant, a term Einstein introduced into his equations of general relativity in 1917 and later called his biggest blunder. Einstein added this term to allow for a static universe, which he thought was correct at the time. When Hubble discovered the universe was expanding, Einstein removed the cosmological constant. But now it seems the cosmological constant, or something very much like it, actually exists. It represents the energy density of empty space, the vacuum energy. Quantum field theory predicts vacuum energy should exist, but calculations suggest it should be enormous, about 120 orders of magnitude larger than what we observe. Why the vacuum energy is so small, yet not zero, is one of the deepest problems in physics. Alternative theories propose that dark energy is not constant but evolves over time, a concept called quintessence. Others suggest modifications to general relativity on cosmic scales might explain accelerated expansion without needing dark energy. So far, observations are consistent with a cosmological constant, but future surveys will test whether dark energy's properties have changed over cosmic history. Dark energy's existence has profound implications for the universe's future. In a universe dominated by matter, expansion would eventually slow and possibly reverse, leading to a big crunch where the universe collapses back on itself. But in our universe, dark energy dominates and drives ever faster expansion. The universe will expand forever, with galaxies getting farther apart. Eventually, distant galaxies will recede faster than light can travel through expanding space, and they'll disappear from view. In the far future, hundreds of billions of years from now, all galaxies outside our local group will have receded beyond our cosmic horizon. The night sky will contain only the handful of galaxies gravitationally bound to the Milky Way. Civilizations arising in that distant era might never realize there are other galaxies or that the universe is expanding. They'd inhabit a very different cosmic landscape than we do. Even farther in the future, perhaps 10 to the 100 years from now, all stars will have died and galaxies will consist only of dead stellar remnants, black holes, and dark matter. After 10 to the 140 years, even black holes will have evaporated through Hawking radiation. The universe will consist of a dilute gas of elementary particles, essentially at absolute zero, in a state of maximum entropy called heat death. This might sound depressing, but it's so far in the future that it's almost beyond comprehension. The age of the universe is currently 13.8 billion years. 10 to the 100 years is incomparably longer. Dark matter and dark energy remind us how much we still have to learn about the universe. We've mapped the cosmos across billions of light years, we understand how stars and galaxies form and evolve, We can calculate what happened in the first seconds after the Big Bang, yet we don't know what 95% of the universe is made of. This is humbling, but also exciting. Major discoveries await. Understanding dark matter and dark energy is one of the central challenges for 21st century physics and astronomy. Let's journey to the most distant reaches of the observable universe, not in space, but in time. The farthest we can see brings us to about 380,000 years after the Big Bang, to a glowing surface called the cosmic microwave background. This is the oldest light in the universe, radiation that has been traveling through space for more than 13 billion years. The cosmic microwave background, or CMB, is a window into the infant universe, giving us a baby picture of the cosmos and revealing the seeds from which all structure grew. The universe began in the Big Bang about 13.8 billion years ago. In the beginning, the universe was extraordinarily hot and dense, filled with a plasma of particles and radiation. It's important to understand that the Big Bang didn't happen at a point in space. Space itself came into existence with the Big Bang, or more accurately, the Big Bang marks the beginning of the universe's expansion. There's no center to the expansion, no place where the Big Bang occurred. It happened everywhere simultaneously. In the first moments, the universe was far too hot for atoms to exist. Matter consisted of a soup of elementary particles, quarks, and leptons interacting with photons of light. As the universe expanded, it cooled. After about 1 second, quarks combined to form protons and neutrons. After a few minutes, nuclear fusion began, creating helium and trace amounts of lithium from hydrogen. This primordial nucleosynthesis determined the relative abundances of the lightest elements, ratios that match observations of the oldest stars and gas clouds, providing strong evidence for the Big Bang theory. But the universe was still too hot for atoms to form. Any time an electron attached to a proton to form hydrogen, a passing photon would knock it free again. The universe remained an opaque plasma, with photons constantly scattering off free electrons. Light couldn't travel far before being absorbed and re-emitted. If you'd been there, you would have seen a glowing fog in all directions, with no possibility of seeing any distance. After roughly 380,000 years, the universe cooled to about 3,000 degrees, cool enough for electrons and protons to combine into neutral hydrogen atoms. This is called recombination, though it's a misleading term since the electrons and protons had never been combined before. With electrons bound into atoms, photons were suddenly free to travel through space without constant scattering. The universe became transparent. The photons filling the universe at that moment have been traveling through space ever since, gradually redshifted by cosmic expansion but never absorbed. These photons are the cosmic microwave background. When these photons were emitted, they were visible light, with wavelengths corresponding to a temperature of about 3,000 degrees. But the universe has expanded by a factor of roughly 1,000 since then, stretching the wavelengths of these photons by the same factor. What was once visible light is now microwave radiation with wavelengths of about 1 millimeter, corresponding to a temperature of about 2.7 degrees above absolute zero. The entire sky glows, faintly with this microwave radiation, the cooled remnant of the hot early universe. The CMB was predicted in the late 1940s by physicists working out the implications of the Big Bang theory. They calculated that if the universe began hot and dense, it should be filled with thermal radiation left over from that early time. In 1964, Arno Penzias and Robert Wilson, working at Bell Labs, detected a mysterious microwave signal coming equally from all directions in the sky. After ruling out all possible sources of interference, including pigeon droppings on their antenna, they concluded they'd detected the cosmic microwave background. The discovery earned them the 1978 Nobel Prize and provided the most direct evidence for the Big Bang. The CMB is remarkably uniform across the sky. In every direction we look, we see the same temperature to an accuracy of about 1 part in 100,000. This uniformity is itself a puzzle. How did regions of the universe that were never in contact, too far apart for light to have traveled between them, come to have the same temperature? The leading explanation is cosmic inflation, a period of exponentially rapid expansion that occurred in the first fraction of a second after the Big Bang. Inflation stretched a tiny, initially uniform region to enormous size, creating uniformity on scales larger than would otherwise be causally connected. Though the CMB is nearly uniform, it's not perfectly so. Temperature variations of about 1 part in 100,000 exist across the sky, creating a mottled pattern of slightly warmer and cooler regions. These tiny fluctuations are incredibly important. They represent density variations in the early universe, regions that were slightly more or less dense than average. These are the seeds from which all cosmic structure grew. Slightly denser regions had slightly stronger gravity, attracting more matter over time and eventually collapsing to form the first stars, galaxies, and galaxy clusters. Several space missions have mapped the CMB in increasing detail. The Cosmic Background Explorer, or COBE, launched in 1989, first detected the temperature fluctuations. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped the fluctuations with much higher resolution. The Planck satellite, launched in 2009, produced the most detailed CMB maps yet. These maps have revolutionized cosmology, allowing precise measurements of the universe's age, composition, geometry, and history. The pattern of temperature fluctuations in the CMB isn't random. It contains information about the physics of the early universe. Different cosmological models predict different patterns of fluctuations. By analyzing the observed pattern, astronomers can measure cosmological parameters with extraordinary precision. The CMB tells us the universe is 13.8 billion years old, with an CMB uncertainty of less than 1%. It tells us the universe is flat, or very nearly so, meaning parallel lines remain parallel forever, and the angles of a triangle add up to 180 degrees. It tells us the universe contains about 68% dark energy, 27% dark matter, and 5% ordinary matter. It tells us the initial density fluctuations followed a specific pattern predicted by inflation. The CMB also shows subtle polarization patterns caused by photons scattering off electrons in the early universe. These polarization patterns contain additional information about the early universe and might eventually reveal evidence of gravitational waves produced during inflation. Detecting these primordial gravitational waves would be a major discovery, providing direct evidence for inflation and a window into energies far beyond what particle accelerators can reach. Looking at the CMB is like looking at the surface of a sphere surrounding us, the last scattering surface where the photons we see were last scattered before traveling to us. Everything we observe in the CMB happened when the universe was 380,000 years old. We're looking 13.8 billion years into the past. We can't see farther because the universe was opaque before recombination. The CMB represents the farthest we can see with light. But in principle, we could see farther with neutrinos or gravitational waves, both of which can travel through the opaque early universe. The cosmic neutrino background, similar to the CMB but consisting of neutrinos, was produced when the universe was about 1 second old. We haven't detected it yet, but future experiments might. The cosmic gravitational wave background, consisting of gravitational waves produced in the very early universe, possibly during inflation, would give us a view of the universe at unimaginably early times, perhaps as early as 10 to the negative 35 seconds after the Big Bang. The CMB is one of the most important observations in all of science. It provides direct evidence for the Big Bang. It allows us to measure the universe's properties with precision. It shows us the seeds of cosmic structure. It connects the smooth, hot, early universe to the complex, structured universe we see today. Looking at the CMB, we're seeing light that has been traveling for almost the entire age of the universe, carrying information from a time when the universe was radically different from today. A time before stars, before galaxies, before any of the structures we see in the present cosmos. We've traveled far tonight. From our starting point on Earth, we've journeyed through the solar system, past stars being born and dying, through the hearts of galaxies, to the very edges of the observable universe. We've explored objects so dense that space-time breaks down and others so diffuse they're barely there at all. We've contemplated dark matter we cannot see, and dark energy we don't understand. We've looked back in time to glimpse the universe's infancy. The observable universe extends 46.6 billion light-years in every direction, a sphere 93 billion light-years in diameter. This isn't the entire universe, just the portion we can see. The universe beyond this horizon certainly exists, but its light hasn't had time to reach us. The universe might be infinite, extending forever in all directions. Or it might curve back on itself, finite but unbounded, like the surface of a sphere. We don't know. What we do know is that the universe is vast beyond our capacity to truly grasp, filled with structures ranging from the subatomic to the cosmic, and governed by laws we're still working to fully understand. When we look at the night sky, we're seeing a tiny fraction of what's out there. The brightest star visible to the naked eye, Sirius, is only 8.6 light-years away. The farthest object visible to the naked eye, the Andromeda Galaxy, is 2.5 million light-years away. Everything else we've discussed tonight requires telescopes to see, often very powerful ones. Most of the universe is invisible to us, not because it's dark matter or dark energy, but simply because it's too faint, or too far away for our instruments to detect. Yet what we've discovered is astonishing. 100 years ago, we didn't know galaxies existed beyond the Milky Way. We didn't know the universe was expanding. We didn't know how stars generated energy. We didn't know about black holes, dark matter, dark energy, or exoplanets. The field of cosmology, the study of the universe as a whole, barely existed. In just 1 century, we've transformed our understanding of the cosmos. The universe is about 13.8 billion years old, but it will last far longer. Stars will continue forming for trillions of years, though star formation will gradually slow as galaxies consume their gas. The Sun has roughly 5 billion years left on the main sequence, eventually becoming a white dwarf. Earth's habitability will end much sooner, in perhaps 1 billion years, as the gradually brightening Sun makes our planet too hot for life. But long before that, humanity might spread to other worlds, becoming a multi-planet or even multi-star species. We might eventually colonize the galaxy, though the vast distances involved make this enormously challenging. Looking farther ahead, after tens of trillions of years, star formation will cease as galaxies run out of gas. The universe will enter the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. After 10 to the 35 years, even these remnants will decay as protons themselves might decay. After 10 to the 100 years, black holes will evaporate. The universe will become unimaginably cold and empty, approaching a state of maximum entropy where nothing interesting can happen. But these timescales are so vast that they dwarf the current age of the universe by factors beyond comprehension. We find ourselves living in a special time in cosmic history. We're about halfway through the stelliferous era, the age when stars shine. We live when galaxies are still forming and merging, when the universe is rich with structure and complexity. We're able to see distant galaxies before they recede beyond our horizon. We inhabit a universe that is neither too young to have developed complex structures nor too old to have lost them. This is what some call the habitable epoch of the universe, the time when life can arise and thrive. Our position in space and time allows us to study the cosmos. We're not at the center of the universe, there is no center, but we occupy a privileged observational position. We can see billions of galaxies, study stars in all phases of evolution, observe the cosmic microwave background, and contemplate the universe's origin and fate. Civilizations arising in the far future, when dark energy has driven distant galaxies beyond the cosmic horizon, will have a much more limited view. They might conclude they inhabit a small, isolated island in an unchanging void, never suspecting the vast cosmos beyond their horizon. The universe has given rise to life, at least on Earth and possibly elsewhere. From the quantum fluctuations in the first moments after the Big Bang arose the seeds of structure. These grew into galaxies and stars. Stars forged heavy elements and scattered them into space. These elements formed planets. On at least one planet, life emerged, evolved, and eventually developed consciousness and intelligence. We are the universe contemplating itself, matter organized in such a way as to ponder its own existence and origin. The questions that drove our ancestors to look up at the night sky remain. What is our place in the cosmos? How did everything begin? What will be the end? Are we alone? We've answered some of these questions and made progress on others. The universe began in the Big Bang 13.8 billion years ago. It will expand forever, driven by dark energy. We're made of atoms forged in stars, part of a vast cosmos containing hundreds of billions of galaxies. Whether we're alone remains unknown, but the sheer number of planets suggests life might be common. Each generation stands on the shoulders of those before, pushing the boundaries of knowledge a little farther. The next generation of telescopes, the Nancy Grace Roman Space Telescope, the Extremely Large Telescope, and others, will reveal the universe in ways we can barely imagine. They'll find thousands more exoplanets, detect the first stars that formed in the universe, study dark matter and dark energy in greater detail, and perhaps discover things we haven't predicted. The universe is not just something we study from a distance, we're part of it. Every breath you take contains atoms that were once in stars. The calcium in your bones, the iron in your blood, the carbon that forms the basis of your biochemistry, all came from stellar furnaces. You are literally made of stardust, and when you look up at the stars, you're looking at your cosmic relatives, the nuclear furnaces that created the atoms that eventually became you. Our journey tonight has taken us across nearly 14 billion years and 93 billion light years. We've seen worlds of fire and ice, stars that outshine galaxies, galaxies containing trillions of stars, voids containing almost nothing, and the most distant light in the universe. We've contemplated the nature of space and time, the origin of structure, and the ultimate fate of everything. The universe is vast, ancient, and strange, operating on scales and timescales that challenge human comprehension. Yet we can understand it, at least partially, through observation, mathematics, and scientific reasoning. As our cosmic voyage comes to an end and you return your attention to your immediate surroundings, remember that you're still traveling through the universe at enormous speeds. You're moving with Earth as it orbits the Sun, with the Sun as it orbits the galactic center, with the galaxy as it falls through the local group, with the local group as it's pulled toward the Virgo cluster. You're in constant motion, falling through curved space-time along with everything else, part of the grand cosmic dance that's been ongoing since the beginning. The night sky is always there, waiting. Every clear night offers a chance to connect with the cosmos, to see light that has traveled for years, centuries, or millennia to reach your eyes. When you look at stars, you're seeing them as they were in the past. You're looking through time as well as space. You're witnessing directly the finite speed of light and the vast scale of the universe. Before we finish, I want to remind you that if you enjoyed this journey through the cosmos, please consider liking this video and subscribing to Nebula Nights. Your support helps me create more content exploring the wonders of the universe. Share this video with anyone who might enjoy a relaxing voyage through space and time. Leave a comment letting me know which topics you'd like to explore in future videos. There's always more to discover, more to contemplate, more to wonder about. Thank you for joining me on this full night traveling through the universe. From the familiar worlds of our solar system to the incomprehensible vastness of the cosmic web, from the violence of supernova to the quiet patience of the cosmic microwave background, we've witnessed the universe in all its complexity and beauty. The cosmos is stranger, vaster, and more wonderful than we ever imagined, and we're only beginning to understand it. Until next time, keep looking up, keep wondering, keep exploring. The universe is out there, waiting to be discovered. Good night and clear skies.